We're back for another episode of Explosions and Fire. We actually did it. So I was on a break to work on my PhD thesis. But now that I'm back, I'm proud to announce I have completed my PhD funding. Hydroperoxide features a very long oxygen-to-oxygen bond, which makes it very reactive and very unstable. In many scenarios, hydroperoxide can oxidize something and then turn back into water, and it is sold as a solution in water. And that's generally not an issue unless we wanted to do something a little bit more dangerous, because water's very good at stabilizing things, very good at absorbing heat. So can we get hydrogen peroxide by itself without the water solution that is in? And perhaps more importantly, can we do that without dying? I think we need to talk about all the different types of peroxide and what they're used for and their different reactivity. It's all a bit confusing, so I'm going to use an analogy just to try and make things simpler. So let's go with the great American pastime, baseball. So 3 to 6% is first base, and it's not that exciting. I mean, it's good and it's useful in some scenarios. It's not really dangerous. The advantage of it is that you can really get it anywhere. You can get it at the local supermarket, and you can show it on TV, you know, even during the middle of the day. It's safe enough. No one's really going to get hurt. 12% is second base. We've got a lot more peroxide here, which is good, but it also comes with its disadvantages. We really should start wearing protection here because you don't want to hurt your skin or anything like that. Second base can be quite damaging to skin, as a lot of people who use it professionally would know, especially over time. It can really start to damage your skin. Third base is 32%. Once again, we step up another level of hazard, and we don't really want to work with this outside of a professional setting or an area set up to mitigate the hazards. Otherwise, you can result in serious injuries. And it is frustrating that going beyond second base is actually banned in most of Europe at early 2020 due to safety concerns. I think you can still go to third base in Europe if you've got a license, but I mean, I don't know. Is that really going to win the war on terror? And that's as far as most chemists will go. Most chemists won't ever make it to fourth base, 70% or more concentrated peroxide. The only people I know that have to deal with fourth base are rocket scientists. The parts of the internet I go on don't really have much information about what it's like. But more importantly, what about fifth base? What about 90%? How do we get to 90%? There is one main way of concentrating hydroperoxide, vacuum distillation. However, it's a little nuts. Contrary to popular belief, I'm not actually insane. I'm not just talking shit about vacuum distillations because I'm very bad at them, although that definitely does come into it. Do you think you'd be able to concentrate hydrogen peroxide by just boiling it, and you'd boil all the water and the hydrogen peroxide, which has a higher boiling point, will stay behind? But it doesn't really work like that. The hydrogen peroxide and the water together have a different boiling point, so they'll boil off together, and also the heat you're providing to the solution will break down the hydrogen peroxide and then boil off that resulting water product. The more concentrated the peroxide is, the easier you will break down the peroxide, so you can't ever reach a high concentration. The idea behind vacuum distillation is you run the distillation under vacuum, so the boiling point is a lot lower, so you don't have to provide as much heat to the solution, so you don't break down as much hydrogen peroxide. The serious downside of this is the material you want, the hydrogen peroxide, is a higher boiling fraction, and this matters because if you have any impurities at all, such as dust or organic stabilizers that have been added into the peroxide, those are going to be concentrated with the peroxide as well. So even under mild heat, that boiling action with all the impurities and your concentrated peroxides is generally a very bad idea. So I just didn't want to do vacuum distillation. We're not doing vacuum distillation. It's too technical. I'm shit at it. It's a bad idea. For once in my life, I'm not doing the hard and fast route that potentially will kill me, but we're going to try and find a safer route. So our alternative method comes from a Russian paper from 2002. What we're going to be doing is taking our peroxide and putting it into a container with a desiccant. This desiccant, the sulfuric acid, is going to pull water from the atmosphere of the container and therefore the hydrogen peroxide and absorb that water, concentrating the peroxide without heating it. The disadvantage of this method is it does take quite a long time, so I think the authors spent 3 days to a week getting the peroxide all the way up to 90% concentrated. I mean, 3 days isn't too bad, right? How long is a Russian day?
Much of northern Russia is blanketed in sunlight nearly 24 hours a day for 2 months.
Okay, so we're going to try this, and luckily enough, I can get 50% peroxide at the local hydroponic store where it's sold for like plants or something. I have some from a long while ago. It's been in the freezer, so we need to check its concentration. Actually, that's a very good point. How do we know what the concentration of the peroxide actually is? I mean, I could do a titration, but I'd give all of you high school flashbacks, and I don't want to do that. So what we're going to do instead is measure the gas volume, right? We can add some permanganate solution to the hydrogen peroxide, measure the amount of oxygen coming off the solution by the displacement of water, and then, assuming ideal gas, ideal temperature, and spherical oxygen in a vacuum, we can work out what the concentration of the hydrogen peroxide was. And this method, even with my shitty equipment, is surprisingly repeatable and consistent, except for one ginormous flaw, which took me ages to find out. And well done if you've already spotted it, because fuck me, it took me far too long. Fucking stare at this for a while. Yeah. What's wrong with it? We'll get to that soon. Okay, we need a very clean container, and this is important because we don't want any surfaces for the peroxide to react with and turn into oxygen around. And also we want a nice smooth outside, I guess. And also we don't want to use plastic because we don't want organic contaminants in our peroxide. So we're using our fancy Teflon beaker here, and then we're going to get some concentrated sulfuric acid, and that's our next consideration. We don't want the concentrated sulfuric acid to mix ever with the concentrated peroxide, especially in this volume, in a sealed container. That will be very bad. They are very reactive together. A mix of concentrated sulfuric acid and 32% hydrogen peroxide is known as piranha solution due to its ability to be able to eat through organic materials. It will turn materials such as paper into carbon, and then that carbon into carbon dioxide. Organic compounds such as sugar will very rapidly react with the piranha solution, generating a lot of heat in quite a violent reaction. Don't want this in a scenario where we can knock over both those containers and they will mix. It's not a good scenario. I think we broke the almond. And finally, we want a vessel they can both go into. And for me, I didn't really want something you could like screw shut or would seal really well. Because if the peroxide suddenly decided to turn into oxygen, it's going to create a lot of gas. And if it's a very well sealed container, that's a bomb. So I've got this vacuum vessel here, which the lid just sort of seals against the metal by the vacuum pressure. It doesn't screw on or isn't held on in any way. So if the peroxide decides to turn all the way into oxygen, for some reason, it's just going to blow the lid off, which will be bad, but it won't shatter the metal or burst out somewhere, which would be catastrophic. We've got our hydrogen peroxide, we've got our desiccant, and we've got our desiccator. So let's run it. Let's put it in there for a week and come back and remeasure the concentration of the peroxide. And after a whole week, we've just gone up in concentration slightly. I mean, sure. All right, well, I mean, we'll just leave it another week and come back, and it's gone up a little bit, I guess. It's not going up very fast.
41 mils of gas.
It's getting there. No, screw it. It's way too slow. We need something more aggressive. We're going to bring out the big guns, phosphorus pentoxide. Phosphorus pentoxide is a very good desiccant because it reacts with water in the air to form phosphoric acid in an irreversible reaction. The downside of phosphorus pentoxide is it's very expensive and hard to get for the amateur. What's up with that? I'm saying that like it's some relatable thing that other people have. What's the deal with phosphorus pentoxide? This does feel like a little bit of a waste using this 20 grams of phosphorus pentoxide. But whatever, we'll put it in there, we'll run it for, another week, another 2 weeks, and it's increasing in concentration. Fuck it, who cares about time? We're doing it, we're actually doing it. It's increasing in concentration, and we're going all the way to 102%. 102? We're now at the point where I've done things wrong. You probably thought the mistake was in the maths, but it's actually in the goddamn chemistry. See? Fuck. Because I was using permanganate, it doesn't react just to form water and oxygen, you get a hydroxyl, whatever. Boring shit. But the point is, you get twice as much oxygen per, hydrogen peroxide. So our starting peroxide wasn't 40%, it was fucking only 20%. And we spent all these godforsaken weeks concentrating it up to the point where it was starting with, and I could just spend $20 getting another bottle of peroxide. Already at 50%. I was slightly annoyed at this. But to be fair, this reaction was burning through one of the things most valuable to me. The thing money can't buy. 40 grams of phosphorus pentoxide. I mean, what's the deal? It's so expensive. However, if we just calm down for a minute, we have a method here that we know works. So let's forget about time. Time's an illusion. Let's go and buy a new bottle of peroxide, and instead of using permanganate, we can just use a suspension of manganese dioxide to work out the gas volume, and the equation works out correctly. Fresh bottle of peroxide, it's not 50%, it's 40%, but it actually is 40% this time. All we have to do is just go about concentrating it. So let's just fucking speed run this. How hard can it be? We just gotta get new phosphorus pentoxide, leave it for a week, retitrate it, more sulfuric acid. I even started running dry argon into the desiccator and doing like pump purge cycles to try and keep the desiccator dry and speed up the drying reaction. More phosphorus pentoxide, leave it for another week, wait for it to stop raining, more phosphorus pentoxide, wait for it to stop hailing. Get the snake out of the house. How did you get inside? The glassware can decide to break. I can't repair that. Teflon. That doesn't matter. It's not slowing us down.
Yeah, whatever.
Every week, come in and titrate it. Okay, I've used up my entire cylinder of argon now. We're out of argon.
No.
It's whatever. Just keep going. The weeks go past and you've got more 4K footage than your computer knows how to store. At 60%, we can see that it generates a lot more heat and a lot more oxygen than the 40% that we started with. And above 70%, we can see the peroxide starting to add to a fire, act as an oxidizer and overcoming that dampening effect of all that water that holds it back at lower concentrations. You can even see the peroxide solution itself take on a bit of a blue coloration at high concentrations, and that's the absorbance of the peroxide in these very concentrated solutions. We can finally start using my good vacuum pump, the actual decent vacuum on the desiccator. I never went to very high vacuums because at higher vacuums the peroxide seems to degas really quickly, which I think would speed up its decomposition. So I was always limited in the vacuum I could go. I could be wrong about this. I could be wrong about many things. I don't know why it was taking so long. The container might have been the wrong shape or the wrong size. Too big, maybe too small. Maybe the seal wasn't very good and water just kept coming in. Maybe the vessels were too big or too tall or not wide enough. There wasn't enough airflow. Maybe the container being metal ruined it. I don't know. I left it for such a long while and it finally got to 90% concentrated.
80 mils of gas. 80.
But there was only 6 grams of peroxide left. But we've got there. We have 90% peroxide made without vacuum distillation, and it only took us 1 Russian day. One of the more interesting things I observed about the concentrated peroxide, once it reached over about 60%, you could see that its aqueous chemistry looked a bit less dramatic. I think that's just because there is less water there to do the aqueous stuff like dissolving manganate to react with, but also there's less water to turn into steam, so it looks a lot less dramatic because it's just generating hot oxygen rather than steam. But even a super concentrated piranha solution, so if we do a piranha solution with 85% peroxide, you'd expect it to really react very quickly, but it actually doesn't react virtually at all unless you give it some sort of stimulation, like you heat it here and then it does react. I'm not sure what that cause of that delay is. I don't know whether you need some sort of water to start the piranha solution reaction. Or something to do with the polarity and actually getting the compounds into the solution to be reacted with. All of this aqueous chemistry limitations don't really apply to combustion though, and this is where it really shines, right? Because you can really start to use that hydrogen peroxide itself as an oxidizer in that fire. So sure, it acts like an oxidizer. We don't have a very much to spare, which kind of sucks, but hey, we've done it. I also have a lot of phosphoric acid now.
Do more.
What?
Just concentrate it more, right?
Like go further in concentration?
I don't know. I just feel like you can do better.
I suppose. So the freezing point of hydrogen peroxide and water mixtures changes depending on the ratio of those two in a shape that kind of looks like this. And you can use this to your advantage to concentrate it, right? If you have very weak peroxide and you freeze it but only let half of it freeze, the stuff that doesn't freeze will be more concentrated than the stuff that did freeze by a small percentage, but it is a difference, right? So if you just collect that liquid and then do it again, freeze it, and then just collect the liquid again, you'll be hopping down that curve, right? You can't get past that V point. You can either go down or up the curve, but you can't hop over the V. Does that make any sense? I'm just not going to explain that bit. you just can't get over it, all right? Fine. So now we're on the 80 to 90% side of the V. What we can do is freeze it a little bit, collect the solid, and throw away the liquid, and the solid will be enriched in hydrogen peroxide. So I tried this at 85%, and I'm using a calcium chloride solution that can get down to about negative 22 degrees in the freezer. And it should have frozen, but it didn't, and I was pretty confused by that. I let it concentrate a little bit more, so now we're at the 90%, and once again, we're trying to freeze it, and it didn't freeze. Even though it's 90%, it should have frozen. I even have some dry ice to make the temperature go down, and even at minus 30 degrees Celsius, it's not freezing. But we got dry ice, so we can go even colder. If you make a dry ice and ethanol solution, we can get down to negative 70, and it doesn't matter the concentration of the peroxide here. Negative 70 degrees Celsius should be able to freeze any concentration of peroxide. Yet we see it doesn't freeze. And this, once again, very confused me until I realized what was probably happening was it was super cooling. Because what we have here is a very pure solution, right? Because not only have we tried to keep it very dust-free, any little bits of dust that have fallen into the solution would just get completely annihilated by the peroxide. So there's nothing for the peroxide to crystallize around. So at this point, I started getting a little aggressive with the peroxide, which is not something you ever want to say. Throwing it around and just encouraging it to fucking crystallize. Eventually it does. And we have crystals of hydrogen peroxide. Once it has frozen, we can take that solid mass out and put it in a higher temperature bath, one that will let half of it melt but keep the other half solid. And we can remove the melted bit and just leave behind the crystals, which would be enriched in peroxide. And we can do this a couple times until we reach basically a solution of nearly pure peroxide. Once again, I wish I had more, but then again, you got to be careful what you wish for, because this is more than 95% concentrated peroxide, and it's not something you want a lot of, because it can just blow up. I mean, that's as far as we can go. We've basically made nearly anhydrous peroxide, right? Like at this point, the peroxide can dissolve in dichloromethane to a reasonable extent, right? There's not much water in the system, and we can have a peroxide in dichloromethane oxidizer, which is pretty scary. Yeah, it's basically anhydrous. I mean, what more can we do?
You can do better than that, right?
What? We've just gone to 6th base. How are we?
Like, add more peroxide or whatever.
I mean, could we peroxide the peroxide? Now we're going to make a molecule called hydrogen trioxide, which looks like this and is an abomination. We once again require the assistance of a device I call the Hell Machine to create this. It's my ozone generator, and for some reason it's got this tag on it, and I can't remember what was going on with it last time I used it.
Oh, Lord.
Oh yeah, I never repaired that. I should probably repair that. Whatever, it's nothing but a load-bearing solder can't fix. Alright, so what this machine is doing is it's taking oxygen from my oxygen cylinder, putting it through high voltage, turning it into ozone, and then we're running that ozone into concentrated hydrogen peroxide of around 90%. And yes, it's going to be at extremely low efficiencies, but the ozone through the concentrated peroxide is going to make a whole host of molecules, not only the hydrogen trioxide, but also this abomination, the HOOO- ion, which is ridiculous, but apparently does exist. I don't know any way that we could prove that we've made it here in solution. I was really hoping we'd generate something that was impact sensitive at the end of this, and I'd be able to set it off with a hammer, but that's not the case, which was a little bit disappointing. Sometimes you get so caught up in avoiding bad scenarios and surviving a procedure that you don't actually stop to think, what is a good scenario? Actually, speaking of surviving the procedure...
Why am I doing this inside? What? Fuck. Why would I do this inside? Think, Tom. What the fuck?
Ozone smells like a lethal radiation dose feels. That's something we can all relate to. You know when you get a lethal radiation dose, you taste the metal, So that's more than 100% concentrated peroxide. I've spent so much of my time not achieving my goals that when I do achieve the goals, I didn't know what to do. And everything decomposed like within a day. So what is there left to do? In fact, I know what we have to do. I'm just gonna put my gear on.
Wait, how do baseball people do things?
Yeah, that's it.
Okay, that was bad.
Is this a run?
Yeah.
Am I winning?
Yeah. Are you taking runs? You can't do that. Okay, so now we're just not playing baseball.
This is baseball.
Oh, that's it. Yeah. Woo! Take some runs.
Baseball. Baseball.
You're not bad.
Not bad, yeah.
Yeah.
I could be a baseball pro.